Hey guys, welcome back to another episode of Stonks Maxxing. It's day 67, so it's been pretty much 2 months now that we've been keeping this going. In reality, I've been skipping a lot of days, so hopefully I'll be able to be more consistent and keep chugging along with the Stonks Maxxing streams. So this may be the final year I can do this. It's my final year at school, so I wonder I guess I just wonder how long I can keep this up for. But today's stream, I kind of want to go over Intel. This is part day. First part was Intel emergency. I don't really remember too much from what happened during the stream. I think that day it was when Intel reported Q2 earnings for fiscal year 2024, and they ended up missing earnings per share by, I think, 20-30%. They missed revenue maybe by 10-15%. And I just thought it was a good buying opportunity because if you looked at the actual book value of the company's assets and equity, it was higher than the market value of the company. So I thought that was an interesting opportunity to buy a relatively cheap company when you're looking at the balance sheet. But that's just one very simple dimension. I think there's a lot of vectors here that we could talk about. And I did end up reading a sort of newsletter or a Substack by Semiconductor Analysis. I think this guy put it in a pretty good way of thinking about not just Intel, but companies in general when you're looking at companies to invest in. I'm trying to forget it. Arthur Lamalt, that's my best guess. I think it starts with an A, ends in an L. His idea was, okay, there's a lot of stuff within a company. A company is a big and complex organization, so there's a lot of things to think about. There's a lot of distractions and rabbit holes you can go into, but what's really a good way to approach investing is to think about first order approximations and second order approximations, maybe even third or fourth, but those are probably not that relevant. First order approximations, these are the things that actually matter for a company. I think in the case of Intel, he mentioned that it's with the client computing group and the data center and AI group. Those are really the two bread and butter business segments within Intel's complete operating business model. The client computing group, that is really the core product line. So it's core product line meaning its actual name, the Intel Core series of chips. So I think what actually happens is you create these CPUs, i9, i7, i5, at the IFS, the Intel Foundry Service. This is Intel's version of TSMC's fabrication plant. So Intel is what's known as, I believe, an integrated device manufacturer, an IDM. It has both a fab and a design arm. So produce and design chips. Going back to the first order approximation client computing group, Intel produces all of the Core series chips, the i9, i7, i5. Those rankings are just based on the actual quality of the chip. I think there's inherent entropy, uncertainty, whenever you're making or fabricating these chips. So not every chip is going to be the same. When there's an actual quality review, that's when the chips get separated into different buckets, i9, i7, i5, i3. The underlying process is the exact same for all the chips though. Okay, so that's one first order approximation. I think the second is the data center and AI chips. So client computing group, this is considered more towards consumer-facing products. So not necessarily selling directly to everyday people, just like me, but more so selling to original equipment manufacturers that produce consumer-facing products. So think of tablets, more so computers. Computers are the big, so like a laptop or a Windows laptop from Dell, HP. Used to be Apple. Apple nowadays has the M1 chips. I don't even think they produce any with Intel. I could be wrong, but I'm 99% sure all of the newer models have the M1, M2, M3, M4 chips. And then the data center and AI sector or business segment is facing more of a business to business. The end customer really is another business that is going to be utilizing some of the data center compute on either AI projects, training, inference, or maybe some type of cloud application that you need to scale on some type of server in a data center. So those are really the two first order approximations for Intel. I think that's what Arthur was talking about in his Substack post. And I think I agree with him. So when you look at Intel's business segment today, I think there's 5. Client computing group is number 1. Data center and AI is number 2. I want to say IFS could be number 3, although I'm not entirely sure. And when I'm ranking these by revenue. I think there's also one for self-driving or automotive. I think that's another sector. So that, I keep saying sector, but more so segment. That's driven by Intel's investment in Mobileye, which is, I think, a chip manufacturer specifically for autonomous driving. I guess the way that those chips are made, I'd imagine they're probably sort of a system on a chip thing where you have multiple, let's say, logic, memory, and maybe even graphics. I don't know if graphics is the right word, but something that can do a lot of matrix multiplications all embedded onto a single chip in order to probably allow a car to implement a self-driving sort of software. Because I'd imagine with the self-driving, it involves a lot of vision. And I don't know exactly how vision models are implemented for these car models. I just remember you have convolutional neural networks, which I guess are for classification tasks. But that involves taking the cross correlations of different layers. There's a term I'm looking for. I guess convolutional layers. You have multiple channels. Yeah, maybe channels is the thing I'm looking for, kind of like the third dimension. Yeah, okay. So that's that. I think in this case, this is where we can start kind of diving into this Intel thing on our own and start building our thesis out. Maybe to start in one sentence. So describe the company in one sentence. So let's say this: an integrated device manufacturer that produces, so that designs and manufactures semiconductor chips for computers and data center. All right, I think that is the probably most basic one sentence. You know exactly what the company does. It's an integrated device manufacturer, designs and manufactures semiconductor chips. What is it for? For computers and data centers. Okay, so let's see. I think I might go downstairs and turn on the AC real quick. It is really hot in my room. Okay, I'm back. Got some leftover Chipotle I'm about to eat. I'm really hungry. Allison, I see you in the chat. Thanks for tuning in. Thank you for tuning in. I also put in some broccoli in here too that I made. Let's go. Broccoli's pretty good. Oh. Missed your chance? What did I miss? Alright, well, see ya. Okay, let me see. So, I don't know how I should structure my notes. First order approximation order approximation. Think about it this way, right? So it follows key drivers. Client compute group, and then data center plus AI. Do you want to download some data from Bloomberg? See if you can do that. Okay. So Intel can essentially be broken down into segments as a first order approximation. Put this here too. Broken down as a second order approximation. Intel can be broken also be broken to, so call this the Intel Foundry Service. Heading 2, so the client compute group. And let's also take a look at the data center plus AI. Okay. Let's see if we can describe the client compute group in one sentence. Design chips that are used in personal computers for everyday use. I think that's maybe the best way. Design chips used for data center servers design chips used for data center servers for hosting applications and I guess running applications, hosting / running. Applications and training / testing, training / inference. I guess AI training / inference. So I guess AI nowadays, a lot of what gets thrown around is really just deep learning. When I think of deep learning, I'm just thinking of a bunch of computations, matrix multiplications, that essentially build out these neural networks. And I think that's pretty much a high-level overview of how all this works. Okay, so design chips in personal computers for everyday use. I think it's a pretty good summary of exactly what it does. Now I wonder if we could break this down further. So key customers then. Maybe like heading 3. So target customer. So client compute group targets the OEMs like HP, Dell, Asus that are in the business of producing computers, so desktops, laptops for everyday consumers. For everyday use. Right. I wouldn't say everyday consumers because when I'm thinking about it, you can also have one of these Dell computers at some type of office for an enterprise. So it's not necessarily just for people or consumers' everyday use, but it could also be used for business as well. So the target customer, the data center plus AI group targets. Yeah, I wonder who's actually buying that. So is it going to be hyperscalers like Amazon, Microsoft, or Google that are going to buy NVIDIA's chips directly and then somehow assemble those server racks? Or does Intel actually sell the racks themselves? I think there's a few players that come into this space. Supermicro Computers is one that comes to mind. I think they do design some type of server racking products. They also do cooling as well, which I think is pretty important for data centers today. A lot of the computations and the loads that these computers are running are pretty intensive, so I think it just jacks up the temperature in the data center. Targets. Yeah, I'll say hyperscalers for now. Not entirely sure. That are looking to build out plus enterprises digital infrastructure for cloud and AI. Yeah, I think cloud is probably cloud and AI are probably the two big use cases here. Let me see if I can find this article then. Austin. So it was in Austin. It was Arthur. Ooh, yeah, this is an interesting one. Mental model plus differentiation. Let's see, here we go. So where does the second order effects thing come in? Oh, here we go. So anything above this, I'll add. So this is, I guess, copy image. Comment. So, oh wait, let's see if we can caption this. Austin lands ship strat mental model of first order model of Intel business. Core. So Core and Xeon product lines are the big money makers of business. Curious to see what this is.
Today, not tomorrow, not next week. Today is the day I hope you will donate to
21 minutes, maybe I'll watch 5 minutes.
Hi, welcome to Talking Tech. I'm your host, Marcus Yam, and today we're going to learn about how Intel processors get categorized. You may have heard of the Core i9, Core i7, Core i5, and Core i3, and we're going to learn about how these different processors get categorized in their different performance tiers. To tell us more about that today is Intel fellow Guy Therian. Guy, thanks for joining me. For those who haven't seen our last video on Turbo, can you tell us about a little bit about who you are and what you do?
Sure, great to be back to talk to you, Marcus. So I'm an Intel fellow, and I currently concentrate in the areas of performance and power optimization, specifically in something called performance segmentation. It has to do with making sure that the right capabilities are in specific Intel products across the price points.
Okay, so you're definitely qualified to tell me how these different processors get categorized. Can you tell me what's that process like? Is it arbitrary? Is it random? How does that all work?
As you can imagine, there are certain price points in the market that consumers want to spend money, right, on certain capabilities. So these price points are translated into capabilities that we offer in our products, specifically performance capabilities, I/O capabilities, energy efficiency, and things like that. And so the different numbers that you mentioned are brands, Core i3, i5, i7, i9, are levels of these capabilities at certain price points that meet the market needs.
Now, of course, between Core i9, Core i7, you can have core counts, graphics, frequency. How do you determine and how do you differentiate which processor goes into which one? You have a wafer, and each wafer gets cut up into separate dies. How do you figure out which one goes where?
So at the highest level, all the processors are the same. With regards to a monolithic design, they're all the same.
Within a generation?
Within a certain kind of generation. So we have certain kinds of dies that are able to make multiple products from those dies. Okay, so we kinds of die.
Okay, this is actually a very good video. Gonna like this one here, but I don't know where I should add this. So maybe in the client compute group for now, because this is directly talking about core. So core product line. Very good video on Intel's spinning process. YouTube. Oops. So, essentially, at a very high, not essentially, I should say, very high level, all of Intel's processors are the same within a generation. And let's see, processors. So processor, microchip, semiconductor. I feel like a lot of these names represent the same thing. When I think of processor, I just think of processing or something that allows processing. Really, what is processing? I think it's just reading a set of instructions and actually executing those instructions. So I think in the case of a computer, a lot of the processing is done within a CPU, so the central processing unit. And I think all of the Intel Core product line refers to these central processing units. Okay. Right, so they are all from same wafer and the same die.
Vectors are the same. With regards to a monolithic design, they're all the same.
Within a generation.
Within a certain kind of generation. So we have certain kinds of.
So I think with this is probably a good example. Say like a IE 10 nanometer versus, I think nowadays the next generation is a 2 nanometer process.
Dies that are able to make multiple products from those die.
Same type of wafer and the same die. So I think the die here refers to a mold that design of semiconductor.
Nice. Okay.
What is a die in processors? Run as a package, okay. These are actually pretty good pictures. Actual design of the processor. Sure, of the processor.
So we have dies that are able to make multiple products from those dies. Okay, so we not every product we sell comes from one wafer, one die on the wafer, but there are a series of these that we can make multiple products from. So when we have those parts cut and from their dies and packaged, then we classify them through something called class tests to understand what their capabilities are. And based upon those capabilities, which vary, because silicon manufacturing does have variance or manufacturing variability in terms of its leakage, its frequency capability.
Okay, so I guess this is an AMD chip, but I think it proves the point or gets the idea across here. Okay. So when processors are made, there actually is a decent amount of variability in them. Sort of like terms of, yeah, what were the things?
Or manufacturing variability in terms of its leakage, its frequency
Leakage. I think this is the amount of energy that sort of, I don't know if the right word is flows, but it just is leaking out of the processor. Leakage, frequency, capability, voltage requirements.
capability, its voltage requirements in order to achieve certain frequencies, etc. We ascertain what the needs are of these parts to run at certain frequencies, their capabilities, including functionality. Sometimes they don't even function at certain frequencies, or sometimes certain cores don't operate. And so once we know everything about the part that we've made.
Yeah, so I guess, what does frequency refer to here? Electrical currents, waves. I don't know exactly what it is.
We decide whether or not that part is a candidate for productization, or it's a candidate to be crushed and go to the silicon graveyard. So recycling. Yes, we don't bury them.
So, okay, this is every time, every processor that Intel tests will go through a sorting process. Mix will go through a sorting process that sorts them based on their capabilities above.
So what you described, I've heard of this term, is it generally called binning? Did you just describe a process called processor binning or silicon binning?
Yes. Internally, we name the process, the classification process, as binning. And so once we decide what's the characteristic support, then we fuse. Fuse is causing it to become a certain specific product.
And at what stage do these things get classified or binned? Can you tell right from the wafer, or does it have to be fused? Does it have to be in a package? At what point do they get designated Core i9, Core i7, Core i5?
Okay, so clearly there's a certain market demand for the price points. Okay, we go out to our customers when we're coming out with a new product. We have a forecast as to what that product will achieve. Most usually it's versus the previous generation product. And then the customers give us a non-committal request for volume, what they think they can sell at certain price points, and therefore certain performance points. And so then what we do is we go through a manufacturing analysis to see if those criteria that they are trying to buy at certain price points can be met through an analysis for the volume that's needed. And if they are, then we lock that in and we head towards manufacturing to meet that need.
Is this process the same whether you're talking about chips for desktops or chips for laptops? Are they?
Yes, it's the same kind of process. There's a set of requirements, a set of volume projections that we need to meet, and we use that in order to determine whether it's manufacturing feasible in order to deliver
Cool.
the volume that's required amongst all our customers. Because the cardinal sin of manufacturing is to tell your customer that you're going to be able to supply them with product, and then in the end, not have that product to supply because of manufacturing issues.
You're talking about forecasting for customers and finding out what they need. Is there a typical sort of distribution that happens out of manufacturing where you can kind of figure we're going to get this many Core i9s and this many Core i7s? How does that work?
It all depends on the criteria that is being specified by the marketing organization in order to make winning products or leadership products across the price points. And so in some cases, the very, very highest price point, therefore probably the highest performance product, it has a certain amount of them that are going to come out of the manufacturing process. So for example, of all the parts that you manufacture, let's call that 100% of all the material that you're going to make. Anything that's less than a projected 10% of that is something that's not assured. Right? Because you can have unknown variation creep into the manufacturing process. And we also manufacture over time, right? So at the beginning, we have a pre-silicon analysis of what we're going to be able to deliver. Then once we get more mature and we start developing material, manufacturing the material, then we can do a post-silicon analysis, and we have more confidence in the amount of parts that we're going to have over the long term that meet certain criteria. But in terms of the top performing parts, or any bin specifically, any product specifically, it's has lower confidence to deliver anything that's less than 10%, because historically we've seen variation happen in his manufacturing processes, and so the lower amount of percentage we project of all the manufacturing yield, the more risk there is that will actually come out in volume. So we don't want to disappoint our customers, so we generally keep to around no less than 10% of the distribution for products. We make exceptions on occasion, but generally we feel comfortable that at 10% we can adapt to changes in the manufacturing over time.
Now imagine that anything below that 10%, especially in the extreme high end that you alluded to, means that there's some really high-end parts, really perfect choice parts there. I know that there's something we do with those. We call those thin bins, but I want to learn more about what that means in terms of binning in a thin bin. What does it mean?
Okay, so sure. So if you think about our highest performing parts today, this is our Core i9 parts. As you can imagine, we're making millions of parts. And the i9 parts, the i9K parts, are a subset of those parts. And the top bin, like I said, is no less than 10% usually of all the parts that we make in a given time period. So, but because there's millions, we have to set a criteria that millions of parts can meet. But like I said, there's manufacturing variation. So within those millions of parts, even for the top bin, there are still variation within that bin. So some of the parts are significantly better than others, even within that top bin. So when you're making millions, you can make hundreds of thousands, 100,000, tens of thousands that have significantly higher performance, but they have a higher risk to manifest into actual parts. Your bet is in there as whether or not they actually come out in the end.
And we had a recent Talking Tech to celebrate the release of the KS series, and I assume KS is one of those thin bin parts. Is that correct?
That's right. So the KS represents the high
Intel KS. It's not even that bad. I thought these used to be thousands. Okay, so I guess this is maybe where the idea of an AI PC comes into play. So this is the Intel Core Ultra 9 processor. Yeah, I think maybe the sort of thesis here behind Intel's thinking is, okay, if you're going to run these local large language models or AI systems on your machine, say just an everyday laptop, then having some type of processor that can do a lot of these calculations for you is maybe a way to go. Yeah. I don't know, right? Because I feel like I'm not super convinced there that people are going to use these AI computers. Just because a lot of the AI interfaces today, the way that we interact with it, it's through a lot of server side API calls. Like when you're talking to ChatGPT, you're not running it on your computer, right? You're just calling an API that's communicating with some data center out in Virginia or Texas. And that's where the actual processing is done. I just don't know if it's going to be directly on our computers. Yeah. I think with Apple, what they're trying to do here is they are trying to do some of the processing, at least a majority of the processing, I think, on device, on just an iPhone. So maybe when you're talking with Siri, when you're asking it questions, I think it queries ChatGPT, and I think that ChatGPT model is on your device. Could be wrong. And then you also have the idea of Apple's private cloud network. So I think that could be another case where you're not going to need your actual device to do the processing for you, but you really can just call an API and let some data center server do all of the calculations or processing for you. Okay. I think heading 3 AI PCs. I personally think this is BS. Lots of AI interfacing because interfacing can be done with API calls. I doubt there would be a need for local on-device processing, right? Okay. Yeah, you know what? I probably would take this as sort of the first order model of Intel. As opposed to, let's see. So X80, okay, I see. They just changed this. So you have your branding, the pretty much manufacturing strategy here, which is winning the next node. I think the node here refers to the generation of chips. And then x86 lock-in. I wonder what he means by this. I think it's the idea that Intel is the original designer of the x86 architecture. Today, not every company uses this, so I think Apple uses an ARM architecture for their silicon chips. And I think when we talk about architecture here, we're referring to an instruction set. The way that I think the lower level assembly languages are constructed for x86 is different compared to ARM, so maybe there's a different assembly language involved there. And I think the way that the instructions are run is different as well. I don't know the exact details. That's a bit of a... Yeah, that one is a bit hard. Okay, let me see if I could copy this. Maybe put this here. Yeah, I like this image a lot. I'm gonna add this. Finish line. So Intel, TSMC. I see. So 1 to 10. So this will be two nodes, two nanometer, and this will be the 1.8 nanometer. IDM, so internal, yes, integrated device manufacturing 2. Let's see. This could be interesting. Okay, this could be interesting. If I go back to January, I guess networking experience, Mobileye. Reducing costs by $3 billion in 2023. Have they been able to do that? Let's see. So from Intel IDM 2.0 webinar. Has this happened? %40 of our headcount, 25% of our OPEX, and more than 9% of our CAPEX. Alright, that's fair. Integrated device manufacturer. Okay. business units drive excessive expedited. Okay, so this one's a bit of relations. Five nodes, 4 years. 5N, 4Y. ARM was there too. Okay, let me see. So I remember seeing in the news somewhere that Intel chip Fireship. Maybe I'll watch the Fireship video.
I've got some bad news. If your cutting-edge gaming rig has an Intel Inside sticker on it, it might actually have a ticking time bomb inside. When we go CPU shopping, the most important spec is not the clock speed, it's not the number of cores or threads, it's not the transistor count, and not the cache size. The most important thing is actually something we fail to think about, the failure rate. We don't think about this because it's not the number inside. When we go CPU shopping, the most important spec is not the clock speed, it's not the number of cores or threads, it's not the transistor count, and not the cache size. The most important thing is actually something we fail to think about, the failure rate. We don't think about this because modern CPUs rarely fail due to manufacturing defects. They're engineered with such a high degree of precision that it makes rocket surgeons look like morons. No matter how good your CPU CPU specs are, it's all precision that it makes rocket surgeons look like morons. No matter how good your CPU specs are, it's all completely pointless if the chip is unstable. Well, Intel's 13th and 14th gen chips can allegedly achieve an impressive 100% failure rate in certain contexts. In today's video, we'll look at the overflowing stack of problems facing Intel chips and find out if it's time to hit panic mode. It is July 15th, 2024, and you're watching the Code Report. For decades, Intel has dominated the CPU chip market. The company was founded in 1968 and gave us the first dynamic RAM chip in 1970, then released the 4004 in 1971, which was the first commercial microprocessor. That later evolved into the x86 architecture, and the company has been printing money ever since. But the gravy train on biscuit wheels is starting to derail. A big problem with the 13th and 14th gen Intel CPUs, also known as Raptor Lake, has been building up over the last 6 months, and it appears nobody knows exactly what the hell is going on, not even Intel itself. The first issues appeared back in February when PC gamers playing games with DirectX 12 and Handbrake started to experience frequent crashes. Initially, the blame was placed on NVIDIA GeForce graphics drivers, but in April, NVIDIA was like, nah bro, and blamed Intel for GPU VRAM issues and told users to contact Intel support. Then Rad Games, which powers compression in Unreal Engine, discovered that high default clock rates and power usage could be leading to silicon degradation and instability. Eventually, the main fix for this issue was to underclock these CPUs at a lower voltage. Shortly after, motherboard manufacturers...
Right, okay, so I think the clock speed or the clock... I remember overclocking is pushing the CPU beyond its sort of predefined limits. I guess clock speed is probably the rate at which the CPU does its calculations. So maybe I'll do calculations slower. Probably uses a lot less energy.
Manufacturers began rolling out BIOS updates with an Intel baseline profile to provide these weak-ass underclock settings, resulting in an estimated 9% performance loss, although Intel itself was not recommending these settings directly. A couple months later, a leaked internal document from Intel said the root cause of instability was an incorrect value in the microcode algorithm associated with the ETVB feature, or Enhanced Thermal Velocity Boost. However, after the leak, Intel denied that this was the root cause, but they did admit that it could be a contributing factor. In any case, a bunch of game devs, like Alderaan, which makes an MMO that lets you live out your dream of being a dinosaur, released a bombshell post alleging that 100% of the time these chips in a cake. Intel denied that this was B feature, or Enhanced Thermal Velocity Boost. However, after the leak, Intel denied that this was the root cause, but they did admit that it could be a contributing factor. In any case, a bunch of game devs, like Alderaan, which makes an MMO that lets you live out your dream of being a dinosaur, released a bombshell post alleging that 100% of the time, these chips will fail every time. They fail for end users, they fail on game servers, they fail for developers, and worst of all, they provide misleading error messages about running out of video driver memory even when they have sufficient memory. And their prescribed remedy is to have Intel recall these CPUs and refund consumers. That's pretty harsh, and it's kind of ironic that these dinosaur guys hate Raptor Lake chips. But companies like Epic Games and Rad Game Tools have also highlighted these issues, and an analysis done by Warframe produced this damning pie chart that showed how Now it's only the Raptor-like chips that are causing problems. To make matters even worse, YouTuber Level 1 Text analyzed a bunch of crash telemetry data from data centers and found that yes, indeed, there is a huge stability problem with these chips. I don't want to spoil the details, so check out his video for a full breakdown, but obviously we've got a big problem here. I've got an Intel chip in my machine, thank God it's a 12th gen, but I'm going to build a new rig later this year, and it's hard to imagine not using an AMD processor at this point. Luckily though, Intel put out a statement that reassured us Intel bros that they're working on it. Although the investigation is not easy, which is corporate speak for we have no idea what the hell is going on. And really I can't blame them, because I don't think I could do a better job making a bunch of electrons dance around on a rock. This has been the Code Report, thanks for watching, and I will see
Yeah, so that's a big, big driver, or sorry, a headwind, not a driver, a tractor for the client compute group. 14th, 13th plus 14th gen Intel processor. Currently facing a problem with the 13th and 14th gen processors. So I think these are probably the core these are called the Raptor Lake processors. Okay, curious to see then what was level 1 text.
My name's Wendell, and I'm here.
Yeah. We're all human, and Rippling's kind of removed that human error and adds that really personal touch.
We all know that Intel's got a problem with the 13900K and the 14900K being unstable. It's been months. Do we really blame gamers for being impatient at this point? I'm not so sure that this is really just a boost motherboard voltage clock problem. I'm starting to think there's something deeper wrong with the chips. I mean, it's Thursday. All I want to do is just play Dwarf Fortress at ridiculously high single-thread clock speeds. I get intermittent problems are the worst to troubleshoot, but it occurred to me, we have another source of crashes. The games themselves. Loads of games have telemetry in them to track their crashes. A data source from the crashes, I mean. So I started digging into that. And what I found will shock you. I'm much less sure that we can fix this with a BIOS or microcode update because I started digging into this and I went on a journey and now I'm troubled. Come with me as we attempt a level 1 tech's armchair diagnostic. It's a level 1 diagnostic, but from the armchair, right? So take that with a bit of a grain of salt. Gonna do that. Well, did you know when you play a game that most of the time it logs usage data? A lot of the times, one set of analytics goes to the marketing team, like how long you're going to play the game, when do you open it, what all's going on with it. But there's another set of data that goes to the dev team around when the game crashes. The game developers will get a crash report, so I reached out to my contact list and I found 2 different people from 2 different games that were willing to give me access to their crash database so I could look around for interesting stuff. Okay, full disclosure, it took a little bit of finagling and convincing because I said, hey, I think this weird thing is going on. And they said, nah, that seems weird. I was like, no, the errors are probably not what you think they are. And they said, you might be right. See, the problem with the way that the 14900K and the 13900K and other CPUs in the 13th, 14th generation are crashing is that they're not super consistent. I needed to know system configuration, playtime, crash rate. I need to know about the population of just people playing the game without errors in order to make suppositions. And these databases are large and they're also rolling. Neither company really hangs on to untagged or untriaged events more than about 3 months. There's some exceptions to that for really outliers, but mostly it's the 3-month time window. The instability is not particular as well. It's not like the ancient problem, the Pentium foof bug. This is a hardware problem, which actually led to Intel creating their whole microcode system so they could patch CPU errata in software. Even the Intel created.
That's cool. History of problems. Pentium foof bug.
Creating their whole microcode system so they could patch CPU errata in software even when you had a hardware problem. In this case, the errors are all over the place. You're even getting GPU errors. GPU errors, yeah, the out of VRAM error that has now become infamous. A lot of armchair experts and forums saying, hey, your game sucks, you've got a VRAM leak, it's got to be you. And that was actually not the case. That is actually a really common error with Intel CPUs that have this problem, out of VRAM error, when you're not actually out of VRAM. And these crashes aren't so bad that, the game totally crashes always. Though we know that users are experiencing worse crashes, things like blue screens and that sort of thing, but we can't get a crash report if the computer blue screens, or at least most of these games are not set up to be able to do that. So there is a little bit of survivorship bias in all of the stuff that I'm talking about today. So again, grain of salt. There's also one operation that's if the computer experiencing worse crashes, things like blue screens and that sort of thing, but we can't. Though we know that users are experiencing worse crashes, things like blue screens and that sort of thing, but we can't get a crash report if the computer blue screens, or at least most of these games are not set up to be able to do that. So there is a little bit of survivorship bias in all of the stuff that I'm talking about today. So again, grain of salt. There's also one operation that stresses the CPU in a particular way, that is decompression. It is a common feature of games. And check out this statement from Oodle regarding decompression failures when we're talking about their game tools. Red V game tools, yeah, check this out. This is an Intel specific thing. Now this decompression library is ubiquitous. It's well used, it's probably nearly bug free. This is a hardware issue that's creating this, and you
Okay, so let's see. Oodle library. Intel is causing some errors here.
You can see that from this bulletin. This article suggests some BIOS changes and some clock changes that'll help users mitigate, and most of these changes are around power and clock settings. Okay, fine. Maybe motherboard manufacturers pushed things too far. Okay, maybe. We'll come back to that. But I've got some big databases here. Let's see if I can find this particular error, the Oodle error. How many decompression errors are there logged in their respective game databases for the past 90 days? Okay, the answer to that is 1,584. How many of those are Intel 13th or 14th generation decompression errors? 1,431. Ooh. What's the next most high CPU with an error? It's an i7-9750H with just 11 instances of decompression failure. What about AMD CPUs? Maybe AMD only saw 4 entries from any AMD CPU, and that's pretty awesome. Don't assume that means that AMD CPUs are better. I mean, I think they are in this particular case. They're not experiencing these kinds of issues, but there could be way less AMD CPUs in this population. We don't know. I decided to check out those things and check out the distribution, and then there's handhelds to worry about. Almost all the handhelds are AMD CPUs. Not all of them, but a lot of them. Okay, so what's the breakdown? Because if we're only working with 5 players on AMD systems, so we need to know, right? Okay, the breakdown between Intel CPUs and AMD CPUs in the crash database was about 70-30 in favor of Intel, which suggests something about 70% of players are using Intel. 60% on NVIDIA, and the rest were among AMD and literally everything else. This is also another instance where it's weird and misleading because, and literally everything else. This is also another instance where it's weird and misleading because, this is game telemetry data from Windows, but sometimes this is actually game telemetry data from Linux. And this reporting tool reports GPUs grouped together in the Linux scenario differently than it does on Windows. And so you end up with some percentage of the 40% of users actually being Linux users that could be using an NVIDIA or an AMD CPU. So 60% really is the floor for NVIDIA GPUs in this scenario, which is weird. I know it doesn't matter for this video. I chose not to clean up the data for GPU distribution. I just wondered something about the population. So we get it. The data here is not super clean, not ideal, and this is also why I think this has flown under the radar a little bit. Fortunately, the rate of errors per unique player was also not super high. There was a small number of people, less than 200, that were suffering tremendously. Don't get me wrong. But like the PC World article, where they had to actually swap their CPUs, I think those 200 people actually would be better off just swapping their CPUs, just getting an RMA. No amount of microcode is going to help those users, I think. For the problem users, I used those as a springboard to look at what other errors their systems had logged, because they'd logged a lot of them. And I saw a lot of I.O. errors, So I.O. errors, the game, these are NVMe errors, but the game doesn't log that. The telemetry tool doesn't look at system errors as a thing that we should log. It just says it can't retrieve a game asset, which is not super uncommon. Like an NVMe error is not really a super uncommon thing. And once again, the population of all systems that had any I/O error grouped by CPU, the percent of Intel 13900K and 14900K were definitely overrepresented. They had a much higher rate of errors in all errors for those CPUs versus any other CPU. It's very odd. The other reason I say that this is odd is because when we're the CPU or the motherboard during their lifetime of play, I think that the more that these CPUs are used, the rate of error is increasing over time. At least I spent a lot of time trying to find a smoking gun here that would look like that, and it seems like there's some data that fits that supposition. But the analysis of that is very hard because the data is not organized in a way to really be conducive to that kind of searching. For the players that play consistently, the number of errors that they are encountering with their systems are definitely increasing over time for those two CPUs. I can say that, at least. And the intermittent problems, they're the worst to troubleshoot. It's like there's intermittent contact in the input polarizers. Somebody sticking iron filing in the CPU vat? Is it some sort of contaminant? I don't know. It's a leathery, burnt bacon enigma wrapped in a mystery. Maybe the problem here is self-inflicted. I mean, that's certainly some of the messaging from Intel. Users are overclocking their system, or motherboard makers are overclocking the motherboard. That's got to be the source of the problem, right? Well, let's use our brain and think about counterexamples of that. Oh, look, on that quest, I did actually find something interesting. It turns out the 13900K and the 14900K do have a place in the data center. They're not just for gaming CPUs, they're also for gaming servers. And guess what? In the data center, most systems are deployed with a motherboard that is based around the W680 chipset. A W-series chipset, not a Z-series chipset. Z-series chipsets for overclocking. Totally different motherboard, totally different power phase designs. Maybe Intel is just rebadging a Z-series and they've been super lazy about it, but I don't think so because it's designed for Xeon. I mean, these are alternative motherboards for LGA 1700 that is different than their desktop class counterparts. And so one might expect that the CPUs would behave differently on these much more conservative motherboards because these motherboards are designed to operate well within the specifications of the CPU. So I set about gathering crash data from thousands of systems already deployed in the data center around the W-series chipsets. And here's a screenshot of one of the systems that had crashed hard and rebooted. Notice a few things on this screenshot. One, the insanely conservative DDR5 memory speed. This may be a result of automatic crashing and the ASUS BIOS backing off on memory speed. Two, ASUS W680 chipset. Like I was saying, I've seen similar crash screens from the Supermicro W680 boards, which is the other game provider. They use Supermicro. One of them uses ASUS. And the crash rate is pretty similar between these two. I mean, the reason these are used is because of the insanely high single-thread clock speed. And for game servers, it turns out it's actually useful. W680 was created to go along with motherboards designed for maximum stability. Neither ASUS nor Supermicro motherboards really support giving tons of extra power to the CPU.
So what is microcode?
The API my team built makes it fast to check into the Capital One Airport Lounge. It's serverless and reusable by other Capital One dev teams.
I'm just glad this lounge isn't serverless.
Oh, we were just talking about you.
Here you go.
Cheers.
Cheers.
That's technology at Capital One.
Okay, we got the latest microcode, at least for the MSI motherboards, that we're going to check out regarding Intel CPUs. This is kind of ahead of schedule, actually. We were expecting middle of August for these microcodes to start dropping. MSI was first, and we tested it. We're going to talk about what kind of performance you may or may not lose and what sorts of behavioral changes there are with Intel's at least 14900K, which is what we tested on. First, time to pay the bills. Falcon Northwest, custom cases available only through Falcon North. Thermal lineup of systems range two-way overnight shift X129. It's actually later or newer than 0x125, which is the code or the microcode that was sort of leaked that Intel was currently testing for the crashing and instability problems regarding your 14th, 13th gen K-SKU CPUs, anything 65 watts and up, which is just about all of them at this point. Spoiler alert, we've already talked about this. If your 13th and 14th gen CPU is already experiencing and exhibiting instability behavior, it's done. It's toast. This code is not going to fix it. That is an Intel problem that they are going to have to figure out how the hell they're going to deal with that. But this is for those of you that have had or have stable CPUs, like mine included at home, has not had any crashing issues, and I've been running it at 320 watt for a long time. This problem does not necessarily plague every single CPU. I mean, the microcode stuff, there's variance in there. So this is for those of you that do not have crashing Intel CPUs and you want to keep them that way. This is theoretically the way that's supposed to work, although I think we're all a little leery of whether or not it's really going to fix the problem and it's not just a band-aid. So long-term testing is really going to show over time if these are going to fix the problems. So we ran the 14900K on our MSI MPG Z790 Carbon 2. Part of the problem with all of these CPU deaths, the microcode. Now the microcode and the ME engine also had a separate installer that we had to run. So it wasn't just the BIOS update across the board on the cores, and so far that's not what we're seeing here. I don't think most of us ever seen. So actual measurable drop in Cyberpunk that I observed, whereas we were getting 1.58 volts prior to it. So this is where we're actually seeing the microcode changes is going to be in single core and maybe low core count type of workloads where those CPUs are staying at a much higher core clock, closer to the 6 gigahertz, which is what you're supposed to get on single and 2 core performance on the 900 SKUs to get 6
AMD's Ryzen 9000 is a true generational step forward. I'm talking bigger level 1 cache, TSMC's new and improved 4nm FinFET process, and a double-digit IPC uplift thanks to its Zen 5 architecture. And the best part? They're claiming they finally got a non-X3D chip that can, on average, beat their GigaChad 5800X3D, all while using less power. As for Intel, well, they're in the middle of an absolute dumpster fire to the point where I actually think the more interesting question is whether Team Red can slay themselves, or whether you should just skip this launch until they inevitably come out with an X3D variant of these chips that is so strong it makes me forget to segue to our sponsor.
MSI. Need a laptop? MSI's got you covered with their summer sale event. Check out their sweet deals on laptops like this Cyborg 14 using the link in the video description.
Because of AMD's staggered launch, we're only looking at the Ryzen 5 9600X and Ryzen 7 9700X today. Compared to last gen, they boost slightly higher and level 1 caches increased, but the other caches are otherwise untouched, as are core counts compared to last generation. However, thanks to TSMC's manufacturing process improvements, AMD has managed to pack an extra nearly 2 billion transistors into these little guys, about 26.5%.
So it seems like, yeah, there is a bit of cycle here. So Linus Tech Tips, YouTube. In the comments, there was something about cycles. Yeah, I'll take this. Okay. That's nice. Probably gonna go shower soon. It's almost 8, yeah. Okay, so going back, we haven't even taken a look at the actual financial statements of Intel. But this is more so high level. I wonder... Yeah, I wonder if there is something I could do from Bloomberg. I might save that for the next episode. I'm gonna have all the data loaded before the next episode, just so I could play around with that. Okay, so when you look at the data center and AI, the core product here is the Intel Xeon chips, I believe. Intel Core i9. See, maybe microcode. Intel Xeon. Jeez, okay. Let me see. There's non-Intel stuff on Xeon. Intel Xeon. See what Linus Tech has to say.
Happy birthday, Marty. Oh, no, you don't. Let me get this.
Ah, thanks. You're too kind.
I've heard that.
Unlimited 2% cash back. The Wells Fargo Active Cash Credit Card.
AMD left the enthusiast community hanging, and I took that personally, because based on their promised upgrade path, I invested heavily in Threadripper workstations, only for AMD to quietly, completely abandon the high-end desktop space that prosumers and small businesses depend on. It's not that they didn't have a socket-compatible successor product, they just made the business decision not to launch it. But what's this? Intel is launching their Sapphire Rapids Xeon W processors, and get this, offering 64 lanes of PCI Express Gen 5 for just $30 more than a mainstream Core i5? Is the high-end desktop back? What else does Sapphire Rapids offer?
Yeah, I guess this is more so computing for the consumer. Let's see. Computext.
Statements in this document that refer to future plans or expectations are forward-looking.
Thank you for having us at Computex Taiwan 2024. You just heard a famous quote from Gordon Moore in the video, and if you looked at that, we actually, with the permission of his family and the magic of AI, we trained a model on Gordon Moore in his 70s and brought that back to life. And this famous quote, "Whatever has been done can be outdone." And isn't that the very essence of Computex? This event isn't just about what's happening today, it's about what's happening next. And the things we'll talk about today will shape our future for years to come. As we've seen time and again, and at the first Computex, which, by the way, do you know when the first Computex was? 1981. And we were working on introducing the next year, right, a technological marvel called the 8286. Yeah, 100,000 transistors on a chip, and that was a big deal at the time. Today, it's a relic, one of those many relics that I worked on in my career, right? As we look now to have 1 billion transistors on a single chip, and even looking to 1 trillion transistors in a single package by the end of the decade. And unlike what Jensen might have you believe, Moore's Law is alive and well. And Taiwan continues to play a central role. Intel has had its operations in Taiwan since 1985, and next year at Computex, we're going to have a little 40-year birthday party for Intel and Taiwan. IT, Intel and Taiwan together. And I want to start with just a big thank you to all of our partners here. Together, we're changing the world again. Let's hear.
We're breaking the barriers between people and AI and discovering incredible possibilities.
Our partnership with Intel builds collective innovation to solve hard problems.
And unleashing creators' potential and enabling business transformation.
From PC to data center, we are building a more resilient supply chain for semiconductor in the AI era.
We're creating AI solutions that drive global progress
for the betterment of our society.
Everywhere for everyone.
We are achieving breakthroughs that will change the world.
Well, what a great group, and I'm just very grateful for the partnership now for many decades. Some of you were younger when we first got to know each other. But our work together is giving rise to the AI era. And when I think about this AI era, I consider it like the internet 25 years ago. It's that big. Every device will become an AI device. Every company will become an AI company. And we see this as the fuel that's driving the semiconductor industry to reach $1 trillion by the end of the decade. And Intel has a unique position in this as the only company that gets to service 100% of the AI TAM, an AI continuum from semiconductors through products, and that starts with the Intel Foundry. And chips are the heart of the global economy, and the world needs more flexible and resilient supply chains. And this has given rise to us creating the world's first system foundry for the AI era. And our foundry business will also drive the next generation of your innovation, but also the Intel products. And today I'm going to focus our attention on the Intel products portfolio and how it is enabling AI everywhere. And as we think about this, it's the most consequential era, potentially, of the extraordinary careers that I and we have been able to have. And when the internet arrived, remember your first Netscape experience? It's like, yeah, man, this morning I got on the internet. Wow. Okay. Now, you're on the internet every minute. Put your phone away. Listen to me, okay? Get off it, right? And if you're a teenager, you're on it like every 10 seconds. It's just become pervasive in everything that we do. And AI everywhere will push the boundaries of what's possible across every human experience. What we do in the data center and cloud, what we do in the edge, what we do in the PC, and everywhere in between. And with open standards, security, sustainability at the center. So let's start with the data center. AI has been central to the data center, and what Intel is doing has been the key to enabling the cloud data center for decades. We have a stunning 130 million Xeons powering data centers around the world. And this is all.
Okay, that is 130 million Xeons powering data centers around the world. Coming from Pat Gill Singlers. Compu text speech in I think 2024. Yeah, when exactly? So Intel Compu text 2024. So this is in June, okay. June 2024. So this is maybe a month before they released their report. All right.
All based is a huge advantage and a huge opportunity for us collectively. Our customers need infrastructure that's scalable and flexible. They need standard platforms to integrate with existing systems to run those decades of software, right? Those exabytes of data that they have in place. And they need an open ecosystem to maximize choice and value. Of course, they also need more compute and performance, greater density, greater energy efficiency, greater server capacity. And this creates a set of issues that they have to deal with as they have more and more demands for those power and energy solutions. And today, we're launching the solution for this next era. Today, we're launching Xeon 6 with E-cores. And we see this as an essential upgrade for the modern data center, a high core count, high density, exceptional performance per watt. It's also important to note that this is our first product on Intel 3. And Intel 3 is the third of our 5 nodes in 4 years.
Intel 3, third generation of 5 nodes, 4 years.
Continue our march back to process technology, competitiveness, and leadership next year. And this enables us to have the choice for high-intensity scale-out workloads for the future. In simple terms, performance up, power down, and drastically fall smaller footprint. So let's just give you some visual demonstration of what this means. And with that, Chuck, if you come on here and.
So I think it was more speed, less power.
What do you have here, Chuck?
Well, Pat, I've got 2 racks here. Now, in this first rack, it is full of Xeon 2nd Gen scalable processors. We've got 20 of them here, all loaded, ready to go. Over here, well, it's basically empty.
Okay, so why don't you do this, Chuck? And I know you didn't get enough workout time in today. I'd like you to fill this rack, right, with the equivalent compute capability of the Gen 2 using Gen 6, okay?
Give me a minute or two, I'll make it happen.
Okay, get with it. Come on, hop to it, buddy. And it's important to think about the data centers. Every data center provider I know today is being crushed by how they operate, how they expand their footprint, and the space, the flexibility, for high-performance computing, and more demands for AI in the data center. And having a processor with 144 cores versus 28 cores for Gen 2 gives them the ability to both condense as well as to attack these new workloads as well with performance and efficiency that was never seen before. So, Chuck, are you done?
I'm done. I wanted a few more racks, but you said equivalent.
Okay, so let me get it. That rack has become this.
It has become that.
Now, there's a lot of leftover space here, Chuck.
There is. I mean, if you're going to imagine a data center, right, you want the best power efficiency possible, but there's all those new workloads you want to run, so less extra space for those.
Well, okay, so we showed it space-wise, but can you give us a demonstration of what this looks like?
Absolutely. Now, depending on who you listen to, the data, the internet is roughly 60 to 80% media.
Yeah, incredible amount of the bandwidth, incredible amount of the workload is media workload.
Exactly. So in the lab right now, I've got 1 2nd gen, and I've got 1 of the brand new Xeon 6s. You can see them up on the screen, and they are transcoding like crazy, right?
Okay.
It's hard to see though, right?
Yeah.
Okay, so let's do a visualization of that in real time. Now, the Xeon 2nd gen, it is doing 56 videos at one time. Xeon 6, however, 144 videos at one time, and doing them much, much faster. So you can see the frames per second each of those, 628 on the 2nd gen, over 2,600 on the Xeon 6. I mean, a 4.2x or up to 4.2x performance gain on Xeon 6.
So this is pretty incredible. What does it mean for every data center? Time to upgrade to Gen 6. Thank you so much, Chuck. And what you just saw was E-cores delivering this distinct advantage for cloud native and hyperscale workloads, 4.2x in media transcode, 2.6x performance per watt, and from a sustainability perspective, this is just game changing. A 3-to-1 rack consolidation over a 4-year cycle, just one 200 rack data center would save 80K megawatts per megawatt hours of energy. And Xeon is everywhere, so imagine the benefits that this could have across the thousands and tens of thousands of data centers. In fact, if just 500 data centers were upgraded with what you just saw, this would power almost 1.4 million Taiwan households for a year. 3.7 million cars off the road for a year, or power Taipei 101 for 500 years. And by the way, this will only get better. And if 144 cores is good, well, let's put 2 of them together, and let's have 288 cores. So later this year, we'll be bringing the 2nd generation of our Xeon 6 with E-cores, a whopping 288 cores, and this will enable a stunning 6-to-1 consolidation ratio, better clean than anything we've seen in the industry. And you can see why Xeon is gaining momentum in the marketplace. And we're hearing from our customers as well. And for instance, eBay, and they're already
performance per watt. So performance metrics plus performance per watt. Customers, so eBay is one.
Seeing 25% performance per watt improvement over competitive solutions, greater than 90% performance per watt improvements over their third-gen installed base. Let's hear from another customer, partner, and key infrastructure software provider, SAP.
SAP.
SAP, we are passionate about building a greener future. Together with Intel, we are crafting solutions that care for our planet. Our collaboration with Intel extends to enhancing the energy efficiency of modern data centers. For SAP HANA Cloud, it is key to provide industry-leading performance and scalability.
Okay, SAP HANA Cloud.
Intel's Xeon 6 CPU with efficient cores is an important and effortless step for SAP HANA Cloud. To optimize performance, in tests on SAP HANA and SAP HANA Cloud, we were able to achieve a similar performance and scalability while reducing the power consumption by up to 60%. Thank you, Intel, for a strong collaboration and trusted partnership over the many years.
Thank you to our friends at SAP, and look at the ecosystem momentum. Simply put, performance up, power down. And that's why Xeon is driving strong adoption across the ecosystem, and more to come. And in Q3, we'll introduce the E-Core's big brother, the P-Core version, Granite Rapids, our next, more to come.
So, oh shoot. Doesn't seem like there's any...
Up, power down.
Okay, Microsoft is on there. I don't see like an AWS or Google anywhere. Yeah, I'll take a picture of those. ZTE Communications. I think that's China, right? I'm surprised they're on there. Customers of Intel, Xeon.
And that's why Xeon is driving strong adoption across the ecosystem, and more to come. And in Q3, we'll introduce the E-Core's big brother, the P-Core version, Granite Rapids, our next generation of the Xeon 6 family of processors. Xeon back on its way in a big and powerful way for the industry and the ecosystem. Thank you very much. More to come. But clearly, the conversation is about AI and how these next generation workloads evolve. And not only can Xeon be part of today's cloud workloads, but critically, your databases already run on Xeon. And increasingly, what we're seeing is that the LLMs are being complemented by real-time database environments, or RAG, retrieval augmented generation. And when you think about it, here we are in year 22 or 23 of cloud computing. And today, over 60% of workloads now run in the cloud, but over 80% of the data remains on-prem. Wow. This is
okay, that's interesting. So, Pat says 60% of workloads are run on cloud, 80% of data is stored on-prem.
Ordinary amount of data that's unmonetized and unleveraged by businesses. Xeon plus RAG changes that. RAG becomes, in our view, one of the most important enterprise workflows, combining your data and databases, many of those real-time time series data, with LLMs. LLMs may be trained on data that's a month, a year, or years old, but combining that with real-time time series.
This is pretty hyped up. I feel like RAG these days. I don't know. I don't know if the full ability is there. Maybe I'm wrong, but it does seem like this is a pretty, how should I put it, hyped up thing and the world of computing right now. Okay, so is hyped. So Pat is pretty hyped on RAG. Yeah.
Embeddings makes an extraordinary combination. And not only is it powerful Xeons like Xeon Gen 6, but it's also being complemented by our AI accelerators, turbocharging that with Gaudi. And customers are looking for high performance, cost-effective Gen AI training.
Okay, so I guess Intel Gaudi AI product line.
and inferencing solutions, and they started to turn to alternatives like Gaudi. They want choice. They want open software and hardware solutions, and time to market solutions at dramatically lower TCOs. And that's why we're seeing customers like Naver, Airtel, Bosch, Infosys, and Seeker turning to Gaudi 2. And we're putting these pieces together. We're standardizing through the open source community and the Linux Foundation. We've created the powerful Xeons like Xeon Gen 6, but it's also being complemented by our AI accelerators, turbocharging that with Gaudi. And customers are looking for high performance, cost-effective Gen AI training and inferencing solutions, and they've started to turn to alternatives like Gaudi. They want choice. They want open software and hardware solutions, and time to market solutions at dramatically lower TCOs. And that's why we're seeing customers like Naver, Airtel, Bosch, Infosys, and Seeker turning to Gaudi 2. And we're putting these pieces together. We're standardizing through the open source community and the Linux Foundation. We've created the open platform for enterprise AI to make Xeon and Gaudi a standardized AI solution for workloads like RAG. So let's take a look. So Diana, what do we have here?
All right, so I thought we'd do a quick demo of that AI appliance that you mentioned.
Okay.
So this is running on Xeon and Gaudi 2 with components from OPEA, such as the Redis.
So this is an open architecture, whatever that means.
Vector database.
Okay.
And we have here an example that's RAG plus LLM. And I should mention that the LLM we're using is based on Lava, which is a multimodal LLM. So that will come into play as we do this demo. So let me start with maybe a quick medical query.
Okay, so this is Xeon and Gaudi working together on a medical query, so it's a lot of private, confidential, on-prem data being combined with a open source LLM.
Exactly.
Okay, very cool.
All right, so let's see what our LLM has to say. So you can see like a typical LLM, we're getting the text answer here, standard.
Okay, wait, so open platform for enterprise AI. I think this is oops.
But it's a multimodal LLM, so we also have this great visual here of the chest X-ray.
Okay, I'm not good at reading X-rays, so what is this?
I'm not great either, but the nice thing about, and I'm going to spare you my typing skills, so we did a little cut and pasting here. The nice thing about this multimodal LLM is we can actually ask it questions to further illustrate what's going on here. So this LLM is actually going to analyze this image and tell us a little bit more about this hazy opacity, such as it is. So you can see here it's saying it's down here in the lower left. So once again, just a great example of multimodal LLM.
So real time, this is how healthcare providers could be taking advantage of AI solutions today with RAG.
Exactly.
Okay, so what else do you got for us?
Okay, well, RAGs, of course, as you said, are great for up-to-the-minute information, also, confidential on-prem data.
Okay.
So, and I know this RAG is super up-to-date. So I thought maybe I would ask it a question I've been wondering about recently.
Okay, what do you got?
Okay, so it actually has to do with the prices of the Gaudi 2 and Gaudi 3 kits. So I figured I'd just ask that.
But those aren't publicly disclosed.
I thought I just asked, what?
Those aren't publicly available information.
Oh.
I guess they are now. Right, did you check with our PR department before you did this?
It just seemed like a great question.
So the price of Gaudi 2, Gaudi 3 AI kits look pretty compelling.
That was kind of cringe. But I respect it. I shouldn't say that was cringe. I respect it. I like that.
This chatbot just broke some news, so let's go a little bit further. Okay. How does it compare with competition?
All right, let's take a look and see. I'm thinking the chatbot knows this as well. It seems to be pretty up to date on everything. So let's take a look and see how we do with competition. Oh, look, it's got an answer for that as well.
Okay, so pretty compelling. So in other words, it crushes the competition.
It looks like it. It's looking great.
Well, I'm really starting to like this chatbot, and thank you, Diana, for an incredible demonstration of real-time database. And as you see, Gaudi is not just winning on price; it's also delivering incredible TCO and incredible performance. And that performance.
Okay, so Gaudi, let's see, it's cheaper, but it doesn't seem like Intel actually has pricing power here, right? Claims it's cheaper than existing AI accelerators. I'm assuming they're referring to, let's say, like NVIDIA H100s. I think this shows that Intel has little to no pricing power. Yeah. Okay, I think with that, I'm gonna stop here. Gonna go shower and then probably make myself some dinner. Oh, it looks nice outside. Maybe I'll go outside for a walk and then come back, refresh a little bit, go get some Chipotle. Getting some emails randomly. Okay, yeah, got some emails about this project for the internship, so I'll worry about that later. But thanks for tuning in, and so far it's interesting to dive a bit deeper into a company. We haven't really done any quantitative stuff. This is purely qualitative, understanding really the first order and second order effects of Intel. I think what we've done so far is we saw that Intel today is really an integrated device manufacturing company. It has a design arm, it has a manufacturing arm, and those two business segments, I wouldn't say business segments, those two arms of Intel, so you have your right arm, your left arm, are coming together to create chips for different business segments. So this is where I'll talk about business segments. Big ones to think about are the client computing group and the data center and AI. So client computing group, these are chips made for, or I guess processors made for OEMs, ODMs, I think those are original device manufacturers, that just make everyday computers for people or consumers to use, maybe enterprises to use, but in an office, not in a data center. And then you have the Intel data center and AI segment. So this is where the Xeon, possibly Gaudi, although I don't know how much market share Gaudi is currently at right now. I don't think it's probably that much. I actually don't know the software environment as well, because I know with NVIDIA, CUDA is a big part of why people end up using NVIDIA GPUs. There's a lot of abstraction that NVIDIA has created for interacting with their hardware, so you don't actually have to worry about maybe allocating a certain amount of VRAM or RAM to a specific core in a GPU. You can do, I think, just like model.CUDA using PyTorch, and it'll do that for you. So those are probably the two big things to think about: Core, Xeon, maybe Gaudi. And then this flows into the customers who actually buy it, OEMs, ODMs, cloud service providers, hyperscalers, and they give money to Intel. So it's 3-step process. And with that, I'm going to end this here, come back, get some data, we'll look into the financials. Okay, peace.